So guys, this is the second lecture of the video that is related to the mathematics of tumor versus normal cells. So you can see in the figure, I have made a mathematical representation of a tumor cell, right? This tumor cell and a normal cell, right? So what are the base differences between the tumor cell and the normal cells from the mathematics point of view, and how you will be able to differentiate it, right? So if you see in the previous lecture, I have already mentioned about uh, uh, Gibbs free energy, okay, and the new mathematical concept which I introduced is related to the formation of tumor and degradation of tumor. So tumor specific equation. Okay, so as you can see, the topology of this tumor, right? Suppose it is having a contour. See, usually what happens is there are no central forces applied to this tumor, right? So that's why the energy dissipation and propagation in the surrounding immune specific cell, as you can see, is different, right? So there would be the possibility of forming azimuthal angles. These azimuthal angles are very much unspecific regarding the symmetry of tumors. Okay, the symmetry of tumors. Since it is a high dissociating energy that surrounds its in tumor cells at a particular frequency, suppose x milli electron volt, right? So with x amount of milli electron volt, it is radiating its energy, dissipating its energy, and when these go to a normal cell that is surrounded by this nuclear clumped tumor, what happens is it's about to change the integrity. Right? So the integrity of this cell starts changing because the energy that has been coming it is trying to destroy its electrons, or you can say the molecules or the integrant molecules or protein molecules that has tried to give it a normal usual shape with normal pathology, biology and metabolism, right? So it tends to disturb this normal cells. So what happens is there is a formation of hyperplastic lesions, right? The first process will be hyperplastic lesions. Then what happens? Dysplastic lesions will be happening, and what would be it be? Right? So dysplastic lesions means outer surrounding and internal surroundings are changing, right? Their fibers, chromatin fibers are changing, but not at the level which is required. So apoptotic boundary is really very high, right? So it has already crossed its threshold. Now what happens is they become high energy molecule. So that's why when a cancer patient is having a diagnosis or second or first stage of cancer, usually LDH levels increase, lactate dehydrogenase level increase, because the simple reason is huge amount of glucose is being made because of the high energy of tumors. They destroy different cells and to take out the ATP synthase and then convert it for their growth and nutrition, right? So in a closed contour, if you can see the clumping and the degeneration of cells, not being able to differentiate it from a dead cells or a living cells, then we have the equation of the Riemannian form where it behaves like a parallel potential surface, and if you apply the similarity theorem as well as the concept of azimuthal theory in that, then it tends to come with this equation, right? 1 by c n closed contour integration from 0 to infinity, since it is increasing and manifolding to different positions and leads to the aggregation of tumor molecules. So the boundary value is infinity. Then the closed point here is z, right? So the closed point here is z, and from z, if there is some space z naught, right? So comparing it and making it an analysis, we got this integral that would help us to understand the rate of change of tumor with respect to the original environment of the cells and the halo surfaces and vacuolar surfaces that leads it to form a Mobius transform. This Mobius like structure transformation could be solved with the initial Cauchy experiments, right? So the small rate and fractional rate of changes of tumor with respect to the biochemical markers and the reactions needs to change different factors, dysplastic factors, hyperplastic factors, then metaplasia also. It is a metaplasia, right? And then leading to carcinogenesis, right? So usually I took the example of neuroendocrine tumor, and they are highly violating in nature. Along with that, they have a high energy molecule, so they form a carcinogenesis and metastasis very fast, right? If I see a normal cell with the integrity and maintain, del D is always going to be 0, either del H minus T del S, and it will form universal law of thermodynamics, right? So it will follow the universal law of thermodynamics. But in case of tumor, when it's depreciating means what? Conjugal depreciation from the cell division. It tends to formation of more conjugates of tumor. Since it is a complex surface, so then its conjugate on the real axis and the normal real axis would be the conjugate, and then it would be forming a real like structure that would be compared with a normal surface, and then we can define how much gradient of change this has in the structure, in the biochemical nature, energetics, enzymatic activity, and formation of carcinogenic activities inside the cells. If you see, this is a normal equation to analyze how much structural changes are there in tumor with respect to normal cells. Now, as I mentioned, the gradient theory also, the rate of change or the gradient of the normal curve of cell along with the tumor cells could be defined with this equation, right? So this equation would help you to find out the gradients difference with the terms of the enzymatic activities, right? So if your Vmax is a velocity maximum for the chemical kinetics, you can, if from the chemical kinetics or enzymatic kinetics, you can get to know that the change in the velocity of the molecules of the enzymatic molecules tends to progress in case of tumor, right? So then if you consider ATP, n times of ATP is increasing in the domain 0 to 9 of a progressive tumor, we usually take the summation out of the ATP. Okay, suppose x raised to the power n plus 1 plus x raised to the power n is a equation of ATP that has been generalized for this tumor, right? So dissipation could be result of the summation of the energy molecules that are going out, right? And then adding up the glucose content LDH1, then effectively we will getting the concentration of each of the volume of titers of ATP, calcium, glucose, and that leads to the systemic generation of new symptoms in the tumor. So if I see with a real and as well as imaginary axis, this tumor migrate in a certain fashion, right? So this mathematics will help you to analyze the chronological movement of different metastatizing tumor related to different dangerous cancers, that could help you to give an information about the characteristics of tumor, and this could help for the further treatment of the tumor with the novel therapy, right? In case of brain tumor, right? So usually for neuroendocrinal tumor, it is the best technique which I have provide you to use it with artificial intelligence and testing the data variables and training the models, and can be a great aspect for defining the change in the tumor specific gene, right? So I am making more videos to make you analyze the bigger picture of mathematics used in the progression of normal cell proliferation to tumor cell proliferation. For that, stay in touch with my videos and everything, and be posting more of them. Thank you.